Hello guys, can you hear me? Okay, okay, I'm seeing myself, I guess. Everything is fine. Okay, how are you doing guys? I'm sorry I was a couple of minutes late. There was some issues, so sorry for that, so sorry for keeping you waited. So, as you know, today we're gonna have a session to solve problems on graph algorithms. We have a lot of nice problems to discuss, and I think it's gonna be super cool, and you're gonna learn a lot, hopefully, from this live stream. So, shall we start talking about the problems? If you're ready for that, please use this emoji. About AdCoder 370, I will tell you about that as well. Later in the stream, I will tell you about that as well. Yes, thank you. So, let's get started. Okay. The first problem that we're going to discuss today is this problem, road construction. Let me send you the link in the chats as well. This is the first problem that we're going to discuss today. It says that a country has n cities. Initially, there is no road in the country. And guys, let me tell you that first, that none of these problems need any prior knowledge other than the things that we've discussed already. I mean, we've already just discussed about DFS, BFS, about bipartite graphs, about only just simple things like simple terminology like passes, walks, cycles. None of these problems need prior knowledge. You just need to, especially they are about ideas. So we're gonna start solving problems from problems with less difficulties, and we're gonna move on to problems with more difficulties, problems that are harder. So the first problem says that a country has n cities. Initially, there's no road in the country. One day the king decides to construct some roads connecting pairs of cities. Roads can be traversed either way. He wants those roads to be constructed in such a way that it is possible to go from each city to any other city by traversing at most two roads. You are also given n pair of cities. Road cannot be constructed between these pairs of cities. Your task is to construct the minimum number of roads that satisfy the above condition. These constraints will guarantee that this is always possible. So, what we want to do, what this problem is saying, what this problem wants from us, is this. We want to draw some edges such that at the end, between each two cities, like X and Y, we can get from X to Y by at most two roads. Either, in this case, by one road, or in this case, by two roads. So, we want to just be able to go from each city to any other city by at most two roads. So there is an important, and we want to add minimum number of edges, minimal number of edges to achieve that. And there are some pair of cities that you cannot add an edge between them. Is the statement clear? Do I need to watch the last streams? If you are not familiar with DFS, BFS, or bipartite graphs, or passes, walks, cycles, yes, But if you are already familiar, that's okay. You don't need to. So it's mostly about if you know those basic terminology. And I believe even if this is the first stream that you're watching, you will be able to understand everything. Even if this is the first stream that you're watching. So thank you very much. Is the assessment clear? If it is, please use this. A star-like graph, maybe. That's a good idea. We'll discuss that. So if you look at it, there's an important and interesting constraint here. N is up to 10 to the power of 3 and m is up to n half. So m is less than n half. So we're going to use it a lot in this problem. By using it, the problem will be destroyed. This video is exactly for beginners. You really don't need anything to know initially. I mean, in order to understand everything that will be discussed in here, you don't really need to know anything. I mean, with just very simple knowledge of graphs, you can understand everything that we're gonna discuss here. But anyway, if you want, you can watch the playlists of the videos of the previous topic streams. If you want, we have done some videos for the beginners. I will send you the link, or if guys anyone else can send the link, please send them. So what I can say in here is that as we saw, m is less than n half. N is up to 1,000 and m is less than n half. So what can I say is that when we want the number of the distance between each two cities to be at most 2, the distance to be at most 2, as you said, exactly the same way that you had the ideas, if there is an edge, if there is a vertex, that is okay with all the vertices. I mean, it has no limits to connect with the other vertices. We know that for some pair of edges, we cannot add an edge between them. But we know that m is less than n half. So, and each edge will cover 2 vertices. I mean, each edge is between 2 vertices. And we can say that 2 vertices, because of this edge, have an edge connected to them. So when we have m half vertices, less than m half vertices, when we have less than m half vertices, what can we say? We can say that each one of them will cover 2 vertices, so there will be, n half. M, which is equal less than n half. We can say that at the end, there will be, let me use this, there will be a vertex that is not connected to any edge. Connected. That is not, let me say it like that is not in any bad pairs. So I made another graph. These are not the real edges of the graph. I said that these are the bad pairs. Let me say it this way. These are the bad pairs. We have m less than n half bad pairs. And we know that each one of these bad pairs are between 2 vertices. So at the end, because they are less than n half, there will be a vertex that is not in any bad pair. So it can connect to any other vertices. So if you choose that vertex, let me write it here. If you choose that vertex, you can connect it to any other vertices. And this way, the distances between each 2 cities will be at most 2. And the point is that if you do this, the number of edges that you have is going to be n minus 1. And n minus 1 is the minimum number of edges that you can have, because you need to make this graph connected. Between each 2 vertices, I mean, when between each 2 vertices there is distance of at most 2, then between each two vertices there is also a path. So they need to be at least a 3. They need to have at least n minus 1 edges. So this way this problem can be solved. Is it clear? Does it make sense? Yes. I mean, you can completely understand this without any prior knowledge. Don't worry about it, you'll see. Yeah. So for example, was this one okay with you? I mean, if you understood it, put a plus in the chat or use this emoji, please. Even if you are a beginner, I try to choose problems that even if you are a beginner, you can understand them well. I mean, they don't need so much knowledge. They are mostly about just figuring out the ideas and the arguments, and using them you can solve these problems. Okay, nice. So, if you don't have any questions about this one, we can now move on to our second problems. We're going to talk about this in future. I mean, right now this stream is going to be about graphs, but for sure in the future we will talk about them. And also, if you want, you can join our Telegram channel or our Discord server, and we can have further discussions there. Let me send you the link of the Telegram channel and the Discord server. This is the Telegram channel. This is the Discord server, and I think I have to also send the link of the topic streams playlist. This is the link of the topic streams playlist if you want to watch. In there you see that there are plenty of videos for beginners as well. So there is nothing needed to know for this stream. That's a very good question. You don't need to know any important thing. I mean, with very basic knowledge about graphs, you can attend this live stream and understand the solutions. I mean, so far I have talked about one of the solutions, one of the problems, and we've solved it. If anyone had any issue with understanding that one, you can say. I think that it seems like there wasn't any issue in understanding it. So, if you are completely okay with that one, we can just now move on to the next problem. Okay. So, let me a practice ladder? I don't think so. So, let's move on to the next problem. Let me first bring it. The next problem is this one, MP Hart's problem. It says that recently Parry and Arya did some research about MP Hart's problems, and they found out the minimum vertex cover problem. They found the minimum vertex cover problem very interesting. So in this problem, don't worry while seeing this term. I mean, this is nothing important, you'll see. It just says that a minimum vertex cover, this is something that this problem has defined. Suppose the graph G is given, subset A of its vertices is called the vertex cover of this graph if for each edge UV there is at least one endpoint of it in this set, i.e. U in A or V in A. So this problem has also defined something as vertex cover for us. It says that a vertex cover is a set of vertices, I mean a subset of the all of the vertices, such that for each edge at least one endpoint of it is in this vertex cover. So for each edge, either both or at least one endpoint of it is in our vertex cover. In other words, in the rest of the graph, there shouldn't be any edge between the vertices of the rest of the graph. I mean, with both endpoints in the rest of the graph. Otherwise, this is not a vertex cover. There's no such edge. So this is the definition of a vertex cover. It's a set of vertices that covers all the edges. Okay, so this is the definition of a vertex cover, and in here it says that Parry and Ari have won a great undirected graph as an award in a team contest. Now they have to split it into two parts, but both of them want their parts of the graph to be a vertex cover. They have agreed to give you the graph, and you need to find two disjoint subsets of the vertices A and B such that both A and B are vertex cover. Or claim it's impossible. Each vertex should be given to no more than one of difference. So basically this problem says that you have a graph, you want to find two disjoint subsets, two disjoint subsets of this graph, like A and B. A and B are disjoint subset of vertices and you want both of them to be vertex covered. Both are vertex covers. You have to find such A and B or claim that it's impossible. Does it make sense? Yes, sure. I can send you the link as well. This is the link. So yeah, sure. I will explain the statement again. It says that we have a graph. So we have a graph. We want to find two disjoint subsets of vertices such that both of them are vertex covers, or claim that it's impossible. And guys, if anyone is watching the recorded version of this video, the link of the problems are also in the description below. And if you are right now in the live stream, I have sent you the link in the chat if you wanted to see it. Okay, is the statement clear now? And the vertex cover is a set of vertices as claimed in this problem. A vertex cover is a set of vertices such that for each edge, one side of it at least is in that set. For example, if this is my graph, for example, just a simple graph, this is gonna be a vertex cover. These two vertices. Why this is a vertex cover? Because if you see each edge, for each edge, one side of it is in our vertex cover. For example, for this edge, both of its endpoints are in our vertex cover, and for the rest of them, one of them is in our vertex cover. So for each edge, one endpoint of it is in our vertex cover. So this subset of vertices that we chose really covers all the edges. So this is a vertex cover. Thank you. Is the statement clear now? Shall we talk about the solution? Okay, nice. So, do you have any ideas initially? All the cycles should have even length. You can check this by building a BFS tree where even levels will be in one part. Nice idea, nice. So what does it mean that all the cycles have even length? I mean, this is something interesting. I mean, all the cycles having even length means something. There's a word for that. In other words, if we take a look, yes, nice. So if you take a look at this graph, I mean, if we have two vertex covers, for example, this is vertex cover A and this is vertex cover B. We know that every edge, for every edge, it should have one endpoint in A and one endpoint in B. Because A and B are disjoint, and we know that they should have at least one endpoint of each edge. So for each edge, exactly one of the endpoints must be in here and one of the endpoints must be in here. And we must not have any edge like this or any edge like this. These are bad. And definitely there is no edges outside of, there are no vertices outside of A and B. Because if there are some vertices outside of A and B, you can instead give them to one of A or B. That doesn't make anything worse. Okay, so if you have some edges outside, it means that these edges have no, if you have some vertices outside, this means that these vertices are not important because there's no edge connected to them. Because all the edges have one endpoint in A and one endpoint in B. This is what they should have. So you can just give it to one of Parry or Arya. You can give it to one of them. And nothing becomes worse. If something is a vertex cover, after doing this, it is also a vertex cover. So we can say that all the vertices, we can allocate all the vertices to A and B. All the vertices are either in A or B, right? And then we can say that all the edges must have one endpoint in A and one endpoint in B. And no edge should be completely in A and no edge should be completely in B. This means that this graph is bipartite. That's the definition of being a bipartite graph. It means that we have two sets of vertices and no edge is completely in one of the sides. All edges have one endpoint in one side and one endpoint in the other side. So our graph must be a bipartite graph. So the only thing that we need to check in this problem, I mean, when we want to find out if we have two vertex covers, it's just enough to find out if our graph is bipartite or not. If our graph is bipartite, if our graph can be splitted into two parts such that no edge is completely in one part, if the graph is bipartite, we can give one of the parts to Parry and one of them to Arya. So, I mean, A can be one side and B can be the other side. So if it is bipartite, it is possible. If it is not bipartite, then for sure it is not possible. Because those two vertex covers, if you consider those two vertex covers, they completely make a bipartite graph. There should not be any edge in one of the sides, and all the edges must be between these two. So this is completely a bipartite graph. Does it make sense? What is the rating of this problem? The rating of this problem is 1500. So now the algorithm in here is to just find out if the graph is bipartite or not, and if it is bipartite, just print the two parts of it. And if you want more explanation, I have discussed once in this topic stream, in the second topic stream on graphs. I have discussed that how we can find out if a graph is bipartite and how to find the two parts of it. Anyhow, if you want, you can also watch that as well. But I will also explain it here. You know, the point is that in order to find out if a graph is bipartite and find out the parts, you just need to have a DFS on vertex V. And what you will do is this. When you have a 4 on all the edges, first you will you have something like col, which is the color of each vertex, or let's call it color. Color of V is either 1 or 2, which means that is it in the first part or in the second part. Initially, all the colors are 0. It means that they are not assigned yet. They are not assigned yet. So you have a 4, when you come to vertex V, you have a 4 on all the vertices adjacent to V, for U on adjacent of V, adjacent vertices of V. And then you say that if color of U was 0, it means that it is not assigned yet. We just set the color of U to be the opposite color of V. So we can see to be the opposite of the color of V. So we can just say color of U is equal to 3 minus color of V. So it means that if color of V was 1, color of U will be 2. If color of V was 2, color of U will be 1. And then call DFS on U. And initially, when you want to call the DFS, each time you choose a random vertex, an arbitrary vertex. Outside of this DFS, you have a 4 on all the vertices. For V on vertices, I showed with big V. It just means, for example, have a 4 on V from 0 to n minus 1, for example, or from 1 to n. You just say that for each V from vertices, you say that if color of V was 0, this is outside of DFS. This is where we call DFS function. If color of V was 0, just set color of V to 1. So you pick an arbitrary vertex that its color is 0, its color is not assigned, you set its color to be 1, and then you call a DFS on V. And this way you will find if the graph is bipartite or not. The issue in here is gonna be if the graph is not gonna be bipartite, we're gonna have this condition. In here, when we reach in here, both V and U must have colors in here. You have to check, you have to say that if color of V, so you know that in here both V and U have colors. You say that if color of V was equal to color of U, then the answer is definitely no. The graph is not bipartite. You can set a global value variable, that a flag that shows if the graph is bipartite or not. Let's say let's call it NBP, not bipartite. This is a global flag that shows that if the graph is bipartite or not. You set it to be true, and it means that this graph is not a bipartite graph. So basically that's gonna be all. So if, for example, we run it on a cycle with 3 vertices, first, it starts from here and sets the color of this one to be 1. Then in DFS, it calls this vertex, and because its color is already 0, it sets the color to be 2. 3 minus 1, 2. Then this vertex calls the DFS of this vertex and sets its color to be 1 again. 3 minus 2. And then when we are in this vertex, we see all the adjacent vertices, and we see that this vertex, it is already assigned, its color is already assigned, so we do not run its DFS, so we don't go in here. But after that, we check if color of V is equal to color of U, and we see that it is, so we can say that this graph is not bipartite. So this graph is not bipartite. MVP will become true. So this is how we can find out if a graph is bipartite or not, and if it is, what are the parts. In this problem, we just figure it out, and afterwards, we just see out all the vertices in group 1 and all the vertices in group 2. There are 2 vertex covers. When our graph is a bipartite graph, we have 2 vertex covers. We can give one part to one of them, the other part to the other one, and both are vertex covers. Does it make sense? Yes, this stream is around 2 hours. Is it clear? No, it's just we want to find out if the graph is bipartite or not, and we have a DFS for that, and we just keep the color of the vertices. Okay, nice. So shall we now move on to the next problem? If you have any questions, do not hesitate to ask your questions here. I mean, that's completely okay. I mean, I just want you to understand everything that we discuss in here. So if you have any questions, feel free to ask them. And guys, anyway, if you like the video, I would appreciate it if you can like it on YouTube and subscribe to the channel. I think that would help a lot. You don't have to do that as always. I mean, I would really appreciate it if you can do it. So, yes, I mean the minimum number of colors to color a graph with no adjacent color vertices have the same color in a bipartite graph is 2. So we just want to, I mean, we do not need to find the chromatic number. I mean, we just want it to be 2. I mean, we don't want to know that what exactly is that. We just want it to be 2. And why 3? You ask why 3? I guess that you mean in here. This 3 is that because my color can be either 1 or 2. I mean, 3 minus x is the complement of x then. If our choices are 1 and 2, our choices are 1 and 2. So the complement of the color is 3 minus that color. Okay, so when our choices are 1 and 2, the complement of the color is 3 minus that color, 3 minus that number. So when it is 1, 3 minus 1 is 2. When it is 2, 3 minus 2 is 1. So 3, the point is that 3 minus x is going to be the complement of x. If x is 1, it's going to be 2. If x is 2, it's going to be 1. So it's going to be the complement, the other color. So that's why I said 3 minus x. But either way, we just want to color it with 2 colors, not more than that. Does it make sense now? Yes, the stream is around 2 hours. Do you want to also code? Do you want to also see the code? Yes. I can show you some code maybe if you want that. However, we should really manage time as well to get to be able to solve all the problems. But I think we can take a look at the code. Let me find a good code to show you. So, yes, nice. This is a very good code that you can see. You know, as you see in here, first he or she is getting the graph n and m, and then x and y, and all the edges. And then we have for I from 1 to n if ans of I. Ans is that color that I was talking about. If ans of I was 0, DFS of I and 1. I will set the color of I as 1 and DFS from it. So ans of u will be color, number of color is plus. I mean, he is storing that how many of that color we have as well. And then for on all the edges of this vertex, if ans of v was 0, just DFS of v and 3 minus color. I mean, this 3 minus color is nothing complicated. It just means that the complement of this color. Instead of this, he could also have an if. He could say that if the color was 1, call the DFS with 2. If the color is 2, call the DFS with 1. But this is way simpler and easier to implement. I mean, instead of having an if on what the color of v is, we just say that, okay, set the color of the other one as 3 minus color. And then else, we know that if that's the case, there's no issue with this edge because v has, u has itself sets the color of v. So there's no issue with the color of u and v. But in the other case, if ans of v was equal to color, cout minus 1 and exit 0, because cout that this graph is not bipartite and exit 0. At the end, we will see out we needed this number of colors because we needed to print the sizes of the two parts. We see out the size of each part, and then we have for on all the vertices. If ans of I was equal to this ID, we see out I. And this way we print those two parts. So this is just a simple code to get accepted from this problem. Does it make sense? Yeah, we will see it very soon. We have to see these things in the problems. So, does it make sense? Okay, nice. So now let's move on to the next problem. Then let me bring it first. Okay, let's move on to the third problem. This problem is the third problem, beautiful graph. Let me send it in the chat as well. 1093D. And this video will, I will put this link in the descriptions below as well, if you're watching the recorded version. So this problem is saying that you are given an undirected unweighted graph consisting of n vertices and m edges. You have to write a number on each vertex of the graph. Each number should be either 1, 2, or 3. The graph must be beautiful the graph becomes beautiful if for each edge the sum of the numbers on the vertices connected by this edge to be odd. I mean, the graph is beautiful if for each edge the sum of the numbers on the both endpoints is an odd number. For each edge, so we want to put numbers 1 or 2 or 3 on the vertices, and the graph becomes beautiful if for each edge the sum of numbers on vertices connected by this edge is odd. So calculate the number of possible ways to write numbers 1, 2, and 3 on vertices so the graph becomes beautiful. Since this number may be large, print it modulo this much. Okay, you have to write exactly one number on each vertex, obviously, and the graph does not have any self loops or multiple edges. So, what does it mean? It just means that we want to put colors 1 or 2 or 3 on the vertices, such that we want, as it said, we want the sum of the numbers on two adjacent vertices. For example, if there's number A on this one and B in this one, on this one, we want A plus B to be odd. So what does it mean? A plus B to be odd. So we want to put colors 1, 2, or 3 on the edges, on the vertices, such that for each edge the sum of the vertices connected by this edge should be odd. First of all, is the statement clear? If anyone has any issues with it, let me know. So odd, yes, nice. These are all very great ideas. Odds plus even is equal to odds. That is complete. Okay, so one side must be odds, one side must be even. Exactly. 1 should be 2 because the only even number is 2. One side should be 2, and the other side must be either 1 or 3. So one side must be 2, one side must be either 1 or 3. If odd length cycle, the number of ways is equal to 0. That's also a great idea. Okay, either A or B should be 2. Awesome. Yes. So when A plus B is gonna be equal to an odd number, it means that parity of A and B, the parity of A and B are different. So one of them must be odd. It means that one of them is odd, and one even. We must have one odd and one even number between A and B. So the even number is definitely 2. And the odd number is either 1 or 3. So for each edge, one side is either 1 or 3, one edge is 2. This is always the case. But the main point about it is that we can say that between 1 or 3 there is no differences. I mean, it's not important that if you put 1 or 3 on a vertex. I mean, on the condition, on the requirements of the problem, nothing will change. If you either put 1 or 3 on a vertex, that is going to be the same, because the parity of nothing will change. So it's like we are free to choose 1 or 3. 1 or 3 are almost identical, but they're just giving us two choices. When we want to count that how many ways do we have, they give us two choices for each of those vertices that are going to be odd. So first, we can set that. First, we can write O and E on the vertices. Some vertices are O, some vertices are E. Vertices that are O means that they are going to be odd. Vertices that are going to be E, it means that they are going to be even. And the point then is going to be, then on each odd vertex, we can either write 1 or 3. On each odd vertex, we can either write 1 or 3. And on each even vertex, we can just write 2. Do you agree with this? So that's going to be all. Okay, that's going to be all of it. So how many ways are we going to have if that's going to be the case? How many ways do we have then? When all the odds are going to be either 1 or 3 and all the evens are going to be 2. So all the evens have only one way. They are going to be 2. But the odds are going to be, the odd numbers are going to be either 1 or 3. Feel free to ask your question in Discord or Telegram. We will talk about that in Discord or Telegram. Yes, we right now have some, the idea is about to help anyone from each level, and we have many topical streams on these things. So you can ask your questions on Telegram or Discord. 2 ways for one edge. Yes, but how many ways in total do we have? Do you agree that the number of ways in total is gonna be 2 to the power of the number of odd vertices? So I show it with 2 to the power of O. Or let's see 2 to the power of odd. Let's say 2 to the power of odd. That is gonna be the number of ways that we have. If we first fix that which vertices are odd and which vertices are even, then the answer is going to be 2 to the power of odd. The number of ways that we're going to have is 2 to the power of odd, because each even vertex must be 2, each even will be replaced by 2, and for each odd we have 2 choices, either 1 or 3, and you can choose any of these 2. So it's going to be, the number of ways is going to be 2 to the power of odd vertices. Do you agree with this? You're welcome. So that's going to be the first thing that we can say. Okay, I will explain it again, no problem. I'm saying that first, we're gonna have 2 groups. We are going to have 2 groups. We are going to have 2 groups of vertices. Okay. We are going to have 2 groups of vertices. One group must be odd. One group must be odd, and one must be even. And each edge, so we have one group that are odd vertices, one group that are even vertices. At the end, some are odd, some are even. And each edge must have one side in these odd vertices and one edge in these even vertices. So we have the two groups of vertices, one odd and one even, and each edge must have one endpoint in these odd vertices and one endpoint in these even vertices. That's the only way that we're gonna have for each edge, that the sum of the numbers on these endpoints are odd. And then the total number of ways is gonna be equal to 2 to the power of the number of these odd vertices. Because for each odd vertex, for each even vertex, you know that it is 2. But for each odd vertex, you know that it is either 1 or it is 3. So for each odd vertex, you're gonna have 2 choices. But for each even vertex, you have only one choice. So that the end, the answer is going to be 2 to the power of the number of odd vertices. Do you agree with that? And yes, definitely, exactly. It's going to be bipartite. I mean, if we choose all the vertices that are going to be odd and all the vertices that are going to be even, then we cannot have an edge inside any of these two parts. I mean, we cannot have any edge with both endpoints in odd parts or with both endpoints in even parts. We cannot these type of edges. For each edge, its endpoints must be in different parts. One in odd, one in even. So our graph must be bipartite. And we want to count 2 to the power of the number of odd vertices for every case of allocating odd and even to the vertices. So yes, if the graph is not bipartite, there's no way that we can split it into 2 parts of odd and even, such that all the edges are between odds and evens. So there's gonna be 0 way. I mean, if it is not bipartite, in any way that we find odds and evens, anyway we do that, at the ends there will be some edge in one of the parts. And that's gonna be bad. So, because the sum of those endpoints is gonna be, I'm sorry for it. Because the sum of those edges, those vertices are gonna be even. So there's no way to do that actually, if it is not bipartite. If it is not bipartite, we have no way. But if it is bipartite, we have to see that in how many ways we can split it into 2 parts of odd and even, and we want to sum up 2 to the power of odd for every such case. So for every case of allocating odd and even, we want to sum up 2 to the power of the number of odds. Does it make sense now? Does it now make sense? Yes, the graph is underrected. Yes, definitely. No, not binary explanation. Right now, so n should be smaller, like MP hard. No. So far, I'm just saying that I want my graph. I haven't yet discussed what is going to be the algorithm. I'm just saying that I want my graph to be bipartite. And when my graph is bipartite, I have some set of odd vertices and some set of even vertices, and I want to add 2 to the power of odd to the total sum, to the power of number of odds for every of those cases, because each odd can be either 1 or 3, but each even is always 2, so the number of evens does not allocate anything to the final answer, but odds will multiply the answer by 2 for each one of them, because each one of them can be either 1 or can be 3. Okay. So, what we can say is that for each case, we have to do this. Now, assume that if the graph is connected, if our graph is connected, What can we say if the graph is connected at the beginning? Well, if the graph is connected, I mean, those two parts will be uniquely determined. I mean, we can define two parts. I mean, if the graph is connected, if you start DFS on one of the vertices, that DFS that we use to find the color of all the vertices, the color of each vertex will be determined. So if the graph is connected, we have some vertices with color 1 at the end and some vertices with color 2. Now we have two cases. Either vertices with color 1 are going to be odd, vertices with color 2 are going to be even. So either we say that we set these ones to be odd, these ones to be even, or it would also work if the first set is going to be even, the first group is going to be even, the second group is going to be odd. We can also say that this one is even, we set this one to be even and this one to be odd. So assume that there are S1 vertices in here and S2 vertices in here. Assume that our graph is connected. So when we do that DFS for finding the parts, all the vertices will find their color. So the vertices will be split into two parts. So now, assume that the first part has S1 vertices and the second part has S2 vertices. How many ways do we have? Two to the power of set 1 plus set 2 to the power of set 2, 2 to the power of odd plus 1. Well, what is odd? I want the rest of you to also tell me about your ideas. Do you know that what is going to be the answer? Assume that the graph was connected, and after doing the DFS, we have these two parts. One of them is S1, one of them has S1 vertices, one of them has S2 vertices. So what is going to be the number of ways then? Well, this was completely correct. No, not 4 ways. This one was completely correct. It's going to be 2 to the power of S1 plus 2 to the power of S2. Why? Because if the first one is odd, if the first part is odd, and the second part is even, then we have S1 vertices that are odd and S2 vertices that are even, right? Then the number of ways is going to be 2 to the power of S1. Because we said that it's about 2 to the power of the number of odd vertices. The number of odd vertices is S1. Exactly, yes. Exactly. And if the first part is even and the second part is odd, it's going to be 2 to the power of S2. So we have two ways. In one of them it's going to be 2 to the power of S1, in one of them it's going to be 2 to the power of S2. So it's going to be 2 to the power of S1 plus 2 to the power of S2. This is going to be the number of ways that we're going to have. Nice. Nice. So yes, as is also said, it's going to be 2 to the power of S1 plus 2 to the power of S2 if it is connected. Now assume that it is not necessarily connected and we might have several parts. I mean, for example, this is the this is one connected component. Each connected component must have two parts. Okay, for each connected component, we're gonna have a DFS, and in that DFS we have we find those two parts. So in each of these connected components, we're gonna have two parts. So now we are gonna have more than two ways. Assume that we have two connected components. There are only these two connected components. If we have more than connected components, then it is possible that if this is part one of this is part two of the first connected component, this is first part, and this is second part of the second connected component, then what we can say is that there's going to be many ways. For example, it's possible that we set this one to be odd, this one to be even, and for example, this one to be even, this one to be odd. or odd even odd even, or even odd even odd, or even odd odd even. I mean, there are going to be 4 ways actually in here if you have 2 connected components to assign odd and even to. I mean, there are 2 ways for each one of the connected components, that which one is going to be odd, which one is going to be even. So the point is that when we have more than one connected component, we can solve each connected component individually. When we can say that when we have multiple connected components, we can solve each individually. And at the end, just multiply all those numbers by each other. So it's like they are really independent of each other. This is my first connected component. This is my second connected component. This is my third connected component. I see that how many ways do each one of them have. For example, if this one have, for example, 20 ways. This one has 12 ways. This one has 18 ways, 18 number of ways to color them. Then at the end, my answer is gonna be 20 ways for this one, and for each one of these 20 ways, this second connected component has 12 ways. So I should multiply it by 12, and for each of these cases, for the first connected components, there are 18 different ways for the third connected component, so I will multiply it by 18. So the point is that I can solve each connected component individually and just at the end multiply these numbers by each other. So the point is that I will solve each part for each connected component. I see that what is S1, the number of vertices in the first part, what is S2, the number of vertices in the second part, and I will add 2 to the power, I will add these 2 numbers to each other, and then the result will be multiplied, my answer will be multiplied by these results. So if I also want to show you my code, this is a code that I implemented many years ago. It's 2018. If you see, we have several cases. So first I calculated what are the powers of 2. I have calculated them modulo this month. And then for each test case, I call the solve function, and each one of them, first I initialize everything, answer is gonna be 1, call of I is gonna be 0, and g of I will be cleared. And then I see in u and v, and I build the graph, and then I have a for each one of them. If it is not colored, it means that this vertex is from a new component. So I need to find out about this connected component, that how many vertices are going to be in the first part, how many vertices are going to be in the second part. So CNT of 1 is going to be equal to CNT of 2 is going to be 0. And then I will call the DFS, and I put the color of vertex I to be 1. And then at the end, I just say that in my DFS, I just find the colors, and I see that how many vertices of each color do I have. So I will add CNT of col of v by 1, and then my value is gonna be 2 to the power of this PW of I was 2 to the power of I. Value is gonna be 2 to the power of CNT1 plus 2 to the power of CNT2 modulo mod, and the ands will be multiplied by this value. And at the end, I will just see out this and. So this value will be multiplied for each connected component, because all the connected components are independent. If this one has A number of ways, this one has B number of ways, in total they have A times B number of ways, because for each of these A cases, we have B cases for the second components. So it's going to be A times B. Does it make sense? Exactly, ands multiplied by 2 to the power of odd, not 2 to the power of odd plus 2 to the power of even. It's always 2 to the power of odd, but the point is that which part is going to be odd. So 2 to the power of the first part plus 2 to the power of the second part. Because it's always 2 to the power of odd, but the point is that which part is going to be the odd part. Yes, exactly. We calculate for each part, and multiply the answer. Disjoint sets. Are you talking about the previous problem or this one? Because the previous one had disjoint sets. If you talk about that for each connected component, if you have more than one way to partition them into one part, no. For each connected component, we can say that for each connected component, let's show it with CC. For each connected component, there is exactly one way. There is exactly one way to partition it into two parts. Into two parts of a bipartite graph. Why? Because if you start from one vertex, it will uniquely determine all the vertices, the color of all the vertices connected to it. All of them will be 2. And they will uniquely determine the color of all the vertices connected to them. They will all be color 1. And they again will uniquely determine the color of the vertices in the next layer. So you see that when you set the color of the first vertex, the color of everything will be uniquely determined. So there's and if you put it to be 2, everything will be reversed. This one will be 1, this one will be 2, this one will be 1, and so on. So when you set the color of the first vertex, the color of all the vertices will be uniquely determined. So there will be exactly one way. I mean, to be, if the labels of the groups are important, there will be 2 ways. Because 2 ways, if you set this one to be 1, for example, if you set this one to be odd, everything will be uniquely determined. If you set it to be even, everything will be uniquely determined as well. So, I mean, the parts are important. For the parts, there is exactly one way. But if you want to label them, it's important that which one we want to call the first part, which one we want to call the second part. Does it make sense? So, yes, for each connected component, there's exactly one way to partition it into 2 parts. So, nice. So, now let's move on to the third problem that we're gonna discuss today. Valera and elections. This is the problem. I send it to you in the chats. I will also put it in the descriptions below. This problem says that the city Valera lives in is going to hold elections to the city parliament, and the city has n districts and n-1 bidirectional roads. We know that from any district there is a path along the roads to any other districts. Let's enumerate all districts in some way by integers from 1 to n. So we have n vertices, the numbers on them are from 1 to n. Inclusive. Furthermore, for each road, the residents decided if it is the problem road or not. A problem road is a road that needs to be repaired. There are n candidates running the election. Let's enumerate all the candidates in some way by integers from 1 to n inclusive. If the candidate number I will be elected in the city parliament, he will perform exactly one promise: to repair all the problem roads on the way from district number I to district number 1, where the city parliament is located. Help Valera determine the subset of candidates such that if all candidates from the subset will be elected to the city parliaments, all problem roads in the city will be repaired. If there are several such subsets, you should choose the subset consisting of the minimum number of candidates. So basically, let me explain it in here. We have a graph with n vertices and n-1 roads, n-1 edges, and it is connected. So what is this graph? This graph is a tree, right? So So we have n vertices and n minus 1 edges, and the graph is connected. So this vertex is a cyclic, yes, exactly, and this is going to be a tree. This is the definition of a tree. If you're not familiar yet with the definition of the tree, this is the definition of tree. A graph that has n vertices and n minus 1 edge, and it is connected, and it is a cyclic. These are three conditions for the trees: having n minus 1 edges and being connected and being a cyclic. These are three conditions for a tree. And the point is, if a graph has two conditions out of these three conditions, it necessarily will have the third condition as well. For example, if a graph has n minus 1 edges and it is a cyclic, then automatically it is connected as well. If it has n minus 1 edges and it is connected, then automatically it's a cyclic as well. If it is connected and if it is a cyclic, then automatically it has n minus 1 edges. So, if a graph has two out of these three conditions, it's necessarily will have the third condition as well. I mean, it's okay with the third condition as well, and it will be a tree. Why we call it a tree? Because if you draw this kind of graphs, it's going to be something of this one. And it really looks like a tree. It's like we have a tree and we have a root of a tree, and then we have several branches that goes down. I mean, this is a graph that is connected and it has no cycles. And if you count the number of edges, it's going to be n minus 1. So, is the statement clear? I mean, I wanted to first give you a summary of the statement, and then if you want, you can also, I can give you a few minutes to read it. So, for now, we have a tree, and we know that some edges are bad. Some edges need to be repaired. Some of these edges need to be repaired. So, and you know that in each of these cities, we have a candidate that if we choose that candidate in that city, it will repair all the cities from that vertex to the root, to vertex 1. Vertex 1 is going to be the root of our tree. I mean, I set vertex 1 to be the roots because everything will be simpler this way. Each candidate will repair everything starting from vertex I going to vertex 1. It will repair everything in that path. So the point is that if you do if you want to find the minimum number of candidates such that if you choose them, all the rows will be repaired. So for example, in this case, if you choose these four candidates, all the rows will be repaired. If you start from them and go to the roots, you see that all the rows will be repaired at the end. Sorry. I had a call from my professor. I will call him after the live stream. So, does it make sense completely? We want to choose some subsets of the vertices such that if we go from these edges, if we go from these vertices to the roots, we can repair all of them, and we want to repair all the bad edges. Okay. Do you want some time to also read this statement by yourself? No, we do not need to choose leaf nodes. But you can. I mean, it can be proven that it won't be worse if you always choose leaf nodes. Yes, these are good observations. So one observation is that we can always choose leaf nodes. It can be shown that it always makes sense to choose leaf nodes. But, I mean, we're going to discuss about these things. if there is a road that if we repair, then we don't need to repair any more roads that lie on the path from that edge to the root. That is also correct. And we should try to take edges or vertices that are far from the roots. Yes. These are very nice observations that we can say. So the main point in here is that, as we said, we just want to choose some subset of the vertices. We want to choose some subsets of the vertices such that if we go from these vertices to the roots and we repair these edges in their path, all the roads that will be repaired. So the idea in here that can be very helpful is this. I say that let's consider all the bad edges. Let's consider that we have a bad edge here. When we have a bad edge, I can say that I can mark these two vertices next to it. So I say that for each bad edge, mark is two endpoints. Mark is two endpoints. So for each bad edge, I will mark its two endpoints. And then I say that now for each vertex, let's see that how many vertices are marked in its subtree. Well, I know that if there is an edge, there is at least one bad edge in its subtree, then those two endpoints of this subtree are gonna be marked. So there will be more than one vertices that are marked in this subtree, right? So if there is a bad edge inside this subtree, the subtree of this vertex, for example, this is vertex V. If in the subtree of vertex V there is one bad edge, one problem edge, then there will be more than one problem edges in there. There will be a problem edge in there and more than one marked vertices in there. So in this scenario, we have more than one. And we know that if that's the case, we should not choose V because it has no reason to choose V. Because we know that there is a bad edge inside and therefore one vertex in here must be chosen. And when one vertex in the subtree of V is chosen, then there's no point in choosing V as well. The next thing we can say is that we also have a case that in the subtree of V, we have no marked vertices. There's always a case that in the subtree of vertex V, there is no vertex that is marked. What does it mean if there is no vertex that is marked? It means that there are no bad edges here, and also the edge from V to its parent is not marked, is not bad. So V is not marked, and nothing in the subtree of V is not marked as well. So what we can say is that in this case, this part of graph is not important at all, and I can remove this. It is not important. This is just some set of vertices such that there are no bad edges in them. So if it is 0, also there is no reason to choose V. But the point is that the only way that it makes sense to choose V is that if there is exactly one marked vertex inside the subtree of vertex V. What does it mean when there is exactly one marked vertex inside? It means that there is only one bad edge, and that is exactly between V and its parents. This way, we can say that V will be marked and nothing inside the subtree of V will be marked. Because everything in the subtree of V, if there was an edge, if there was a bad edge, then it had its two endpoints to be marked. So there would be more than one vertices. So the edge should have only one side in the subtree of V, and the only edge that has only one side in the subtree of V is the edge from V to its parents. Therefore, we can say that in this problem, we can say that in here, only V is connected to a bad edge, and only in this case is it makes sense to choose V. And if you take a look at what is happening, what is really happening is that for each bad edge, I mean, at the end, what I'm going to do is that for the bad edges, if below them there are some other bad edges, they are not important, and I will remove them. But for the bad edges that are remaining, I'm choosing the vertex below the other one. So in other words, I mean, the only thing that is happening is this. For each edge, I just mark its two endpoints. At the end, for each vertex, I see that I will calculate that in its subtree how many vertices are marked. For each edge, I will mark its two endpoints, and I see that for each vertex in its subtree how many vertices are marked. And if the number of vertices that were marked in the subtree of each vertex V was 1, I will choose that vertex. That's going to be all for the solution of this problem. So for each edge, I will mark its two endpoints. At the end, if in the subtree of a vertex there was only one marked vertex, I will choose that vertex. Does it make sense? That's going to be the simple solution for this problem. Just for each edge, for each bad edge, mark its two endpoints, then for each vertex V such that there is exactly one marked vertex in its subtree, choose that vertex. This is a very clean way to solve this problem. Does it make sense? So if you look at it, if you look at what is it really doing, is this. I mean, what it's doing is that for each vertex V, it just says that in the subtree of V, if there's only one marked edge, it means that one marked vertex, it means that the only bad edge is from V to its parent. And if we choose vertex V, and there's no reason to, so when we have this edge, we have to just choose something from the subtree of V, because we need to cover this bad edge. And since we can choose any of them, and since there's no difference between them, we just choose V itself. And we do not choose more than one vertex from here. The point is that if in the subtree of vertex V, the count is more than 1, it means that there is a bad edge inside. So we don't need to worry about it. So the point is that we do not choose this one, because anyway we have to choose from inside of it afterwards. So there is no point in choosing V. At the same time, if we have in the subtree of vertex V, there are no marked vertices, it means that there are no bad edges in the subtree of V or in the edge from V to its parent. So this part is not important at all. So when it is 0 or when it is more than 1, we do not choose vertex V. When it is the only case that makes sense to choose vertex V is when this sum of the number of marked vertices in the subtree of V is exactly 1. Only in that case we will choose vertex V. Is it clear? Yeah, sure, I will do more of these live streams. So now the only question is that how to find out how many vertices are marked in the subtree of vertex V. In the subtree of vertex V. That's the question now. How we can find out that how many vertices are marked in the subtree of vertex V. Yes, you can ask me any question. And thank you. So how can we find that out? We can just define some variable like count of V is that how many vertices in the subtree of vertex V are marked. So when we want to find out the count of V, so count of V, that means that how many vertices are marked. First, when we do the DFS of the children of V, we find out the answer for the children of V. So the count of those vertices are going to be updated. So it's just enough to add count of those children to count of V. So when we are doing DFS, when we do a DFS on V, and we first set count of V to be equal to mark of V. I mean, if mark of V is 1 or it's true, count of V will become 1. If mark of V is not true, count of V will be 0. So initially we just care about V itself, and then when we find out the children, for the children of V, let's say for the children of V, all the vertices that are connected, I mean by the children I mean these vertices. For example, I'm on this one, the children are these ones. So I have 4 on the children, and I say that for you on children of V, I say that just do the DFS on you and then count of V plus equal to count of U. This way I find out that how many vertices are marked in the subtree of in each vertex, and then at the end, if count of some V was 1, I just stay out that vertex. That's a good question. As I said before, you can also ask this question in our Telegram channel or our Discord server. There are also a lot of people there who can help. But as all, I believe that you should solve a lot of problems. This is a long-term process. If you want to be good at something, this is going to be a long-term process. You cannot get good at something at one night. You have to spend so much time in long-term to be able to solve problems. So just your vision must be long-term. I mean, you should not believe that. I mean, for any sort of growth, and anything, if you want to have growth, you should think long-term. And you need to solve so many problems, and step by step you will improve. I mean, at each step you have to solve so many problems with that difficulty, and when you are confident that you can solve problems with that difficulty, you will move on to the harder problems, to the harder tasks. So that's basically I believe in. The most important thing is that you need to look at it in long term. I hope that it can answer your question. So. Okay, is the solution to this problem clear? Shall we move on to the next one? Okay. So let's now move on to the next problem. The next problem that we're going to discuss today is this problem X or 3. This problem says that Lahov is very proud of his recent discovery, propagating trees. Right now he invented a new tree called XOR tree. After this new revolutionary discovery, he invented the game for kids which uses XOR trees. The game is played on a tree having n nodes numbers from 1 to n. Each node I has an initial value init of I, which is either 0 or 1. The root of the tree is node 1. One can perform several operations on the tree during the game. So far we are playing a game on a tree, and the tree have n nodes numbered from 1 to n. Each node I has an initial value init I, and the root of the tree is node 1. So the only available type of operation is to pick a node x. Right after someone has picked node x, the value of the node x flips. The value of sons of x remains the same. The values of sons of x flips. The value of sons of x remain the same, and so on. So alternatively, the values will change. The values will flip. The value of v remains the same. The values of sons of v, the value of v will change. The value of sons of v will remain the same, but the value of sons will change, and so on. The goal of the game is to get each node I to have value goal of I, which can also be only 0 or 1. You need to reach the goal of the game by using minimum number of operations. We have this tree. It is a rooted tree. The root is vertex 1. Each time we can choose a vertex v, and if we choose a vertex v, then the value of v will flip. The value of the children of v will not flip. But the value of the children of v will flip. These values will flip. Then the values of children of v will not flip. They will remain the same, but again in the next level it will flip. So the point is that alternatively it will flip. If we look at each height, alternatively these values will flip. So now the point is that if we do this, we have some initial value for each node, and we have some goal for each node. We want to find out the minimum number of operations needed to reach the goal of each vertex. Is it clear? Is the statement clear? And have I sent the link to you? Let me also send the link of this problem to you. This one is the link of the problem. I will also put it in the descriptions below this video. Okay, so do you have any idea so far about this one? Can you say any facts? Let's talk about facts. What are the facts that you can say in this problem? What are the facts? Let's consider some scenarios. For example, let's say that for the roots, for the vertex 1, assume that init of 1, the initial value of roots vertex 1 is not equal to the goal of vertex 1. What can we say in this scenario? Can you say any facts? There's something that we can say for sure. Exactly, we have to flip the roots in that case. In this case, we have to flip the roots. So, if init of 1 is not equal to goal of 1, we have to flip roots. The roots. In this case, we have to flip the roots. But what if they are equal? If init of 1 is equal to goal of 1. Let's use it. What can we say then? Is there any facts that we can say for this case if init of 1 is equal to goal of 1? There's no need to flip, we may or may not flip, but I argue that we should not flip. That is my argument. I say that we should not flip in that case. If init of 1 is equal to goal of 1. Well, the point is that when you flip, first of all, I say that we never will flip the same vertex more than once. Okay, one of the facts that I can say is that we never flip the same vertex more than once. Because the point is that if we do it twice on a vertex, it has no effect on anything. Some subset of vertices will change and then they will change back to the beginning state. I mean, so nothing will change, nothing will happen. So if you flip some set of vertices, if you flip a vertex twice, it has no effect. So if you do it x times and x is greater than 1, you could instead do it x minus 2 times. The last 2 times did not have any effect. That's a contradiction. It means that it was not minimum. So we will never do it more than once. Okay, so by saying that, we showed that if we do it twice, it has no effect. So now, by saying that if we have done it x times on some vertex and x is greater than 1, instead of x we could do it x minus 2 times, and that would have the same effect. So this is a contradiction. It means that we didn't do the minimum number of operations. So in our final answer, we never do operation on a vertex more than once. So the point is that now for each vertex we either flip it once or we do not flip it at all. Now if you flip the roots, then there's no way to get it back to what it was. Okay, if we do the roots, if we flip the roots, there's no way to put it back to what it was. So in that case, we can say that if init of 1 was equal to goal of 1, we can say that we must not flip the roots. Does it make sense? Yes, about yesterday, I'm really sorry. I mean, there was some issues that I couldn't do that, and I'm really sorry for that. I hope that I didn't keep you waited. I hope that that would never happen again. I'm really sorry for that. Did I keep you waited? Sorry, anyway. What if many child of roots don't match the... Well, the point is that we cannot. The point is that we cannot change the roots. It doesn't matter if the children of roots don't match, then we need to flip them. They need to do something by themselves. Roots cannot do anything for them, because if the roots will be flipped, then its color will not match the real color of that vertex. Of the root. So roots cannot help. Thank you. It seems better. So the question is that what if many children of root don't match with their goal? Isn't it better to flip root instead of all the children? Maybe it's better for them. But the point is that the root cannot do that. Because if the root does that, its own color will not match with its goal. So at the end, we want the color of all the vertices to match their goal. If the root will flip, then it cannot match its goal. Okay, and we showed that it will either be flipped once or will not be flipped. It will not be flipped more than once, because if you flip it twice, it's like not doing anything. So if you flip it odd number of times, it's like you're flipping it once. If you flip it even number of times, it's like you're not flipping it. So the point is that the root cannot do anything for them, because if you choose the root, the color of the root will mismatch the color that it must have. Exactly. Yeah. If the goal of I not equal to init of I number of flips before it in the past is odd. Exactly. Yeah. So the point is that we can extend it. So the point is that for the roots, it will be uniquely determined if it will be chosen or not chosen. So we know that what is the case for the roots. Then when we go to the children of the roots, can we say the same thing again? Can we again say that uniquely determined if they're gonna be chosen or they will not be chosen? We can kind of say the same thing about the children, because for example, for this child, again, first of all, I know that root has no effect on it because root changes the sons of sons and not its son. So again, we can say that if init of I not equal to goal of I, it must be flipped, otherwise it must not be flipped. Okay. So these will be uniquely determined as well if they are going to be chosen or they're not going to be chosen. Again, for the children of these vertices, again, they currently have some value. Their value might have been changed by the roots. But anyway, they have a value right now. It is changed or it is not changed. Anyway, when we get to this vertex, it has a value. Maybe root has changed. Maybe initially they were 0 and now root has turned them to 1. Or maybe they were 1 from the beginning. It doesn't matter. It means that they are right now 1 or they are right now 0. If what they are currently is not equal to what they need to be, if what they are currently is not equal to what they need to be, we need to choose them again. So the point is that whenever we get to a vertex, all its ancestors are decided. So when we get to a vertex like V, all its ancestors, assume that all the ancestors are decided. The point is that no, V has some numbers, V has some value that might be affected by its ancestors. By choosing, then we know that by choosing vertex V, its value will be flipped. We just need to see, does it need to be flipped or it does not need to be flipped? We need to see that what is its value right now, what its value must be. And if they're not equal, we need to choose this vertex V. If they are equal, we should not choose vertex V. So again, this vertex V will be uniquely determined as well. So the whole point is, we can just do it in a greedy way. It's unique. It's not even greedy. It's just unique to find out if each vertex will be chosen or not be chosen. You just need to have a DFS. Whenever you got to a vertex, you need to find out if its value has changed or not. And this way you can see that what is its current value, what is its goal, and this way you can easily find out what is going to be the answer. And if I show you my code as well, it would be easier to understand what we're doing. So this is the whole code. I've implemented this in 2015. So it's a lot of time ago. So my code is a bit weird. I used to, for example, define fors, etc. This it is not very clean code. I just show you to see that how I was coding around 9 years ago, and how this problem could be implemented. So in this problem, you get a number n, and you have a for, and you get all the edges and make your graph. You store your graph in computer, and then get in it and go and do a DFS. In your DFS, you have a vertex, and you have two booleans. F1 states if the vertex in the current height is flipped. The point is that only heights matter. When you change something, the vertices in the next height will not change. The vertices in the next height will change. Again, in the next height will not change. in the next height will change, in the next height will not change, and so on. Right? So alternatively, they will change and they will not change. So f1 means that if the vertex at this height is changed, f2 means that if the vertex at the next height, at the other height, is changed or not. These are the definitions of f1 and f2. So if f1 is set, it means that I have to change init of var. Init of var becomes equal to 1 minus init of that vertex. And if init of vertex was not equal to the goal of the vertex, I will push back this vertex to my ans. I just added 1 to make it 1 base. I could also just add 1 whenever I wanted to print. That was maybe better. And then flip f1. Because if f1 is already 1, now that I'm choosing this vertex, it should become 0. If it is right now 0, now that I'm choosing this vertex, it should be 1. And then I have a 4 on the adjacent vertices, and I say that if they are not visited, in other words, if they are the children of this vertex, because this is a tree, just do a DFS on that vertex. This time, first pass f2 and then f1, because we are going to the next level. Now, f2 is the current level. f2 is the current level now when we go to the children, and f1 is the other level. So when we go to the children, we DFS of edge of var and I, and f2 and f1. And this way we can find out if each vertex must be changed or not. And if you just do this simple code, at the end you will get an accepted vertex. Doesn't make sense? Is it clear? That's what we did. We have a little bit of time. I would like to solve the last problem as well if we can. I think we're gonna have many other streams for the graph as well. I have in mind to do one other problem solving session on DP in our next session that is gonna be in a few days. And then in the next week, we are gonna come back to both DP and graphs as well. We are gonna have a lot of sessions. And we have voting for choosing the topics in our Telegram channel. So if you want, you can join our Telegram channel. Let me share the link of the Telegram channel with you again. This is the link of the Telegram channel. If you want, you can join there. In there, I sometimes put votes. I sometimes put votes to find out the topics of the topic streams, and you guys can suggest that what helps you the most regarding the live streams and also the videos. You can always suggest that what you want to be covered. I would love to do whatever you guys want. So, was the solution to this problem clear? If so, we can move on to the next problem. So in this problem, the point was that if you start from the roots and go downwards, you can find all the vertices, that must be changed. Will you do yesterday's article? I think it might be a little bit late for that contest. I don't know. Unfortunately, we missed it, and I was so sad about it as well, but it would be a bit problematic. But if you really need it, let me know. If you really need that round, let me know. Maybe we can do something. Okay, let's now move on to the next problem, to the last problem, and the most challenging one of today's session. Expanding stacks. This problem is from gym. It was a gym that we participated in it very recently, and we had this problem. We faced with this problem. This problem is saying that we have some numbers and two stacks. You know that in a stack, when an element arrives, let me also share the link. Did I send you the link? Okay. So it says that we have two stacks, and we have some numbers that are coming and they're going out. And we know that in a stack, the last item that arrives leaves first. So the point is that you have two stacks. You have to say that if you can, this plus 2 means that 2 has arrived. This minus 2 means that 2 has left. And we have n elements in total. N is up to 1,000. And xi's are from 1 to n. And for each one of them, it arrives somewhere and it goes out somewhere else. And you have to say that if it is possible, that allocate these arrivals to these two stacks such that this makes sense. For example, if we have only one stack, this one makes sense. 2 arrives, then 1 arrives, then 1 leaves, and then 2 leaves. In here, first 1 arrives, and then 2 arrives, and then first 1 leaves, and then 2 leaves. So they cannot be from the same stack. But it makes sense if the first one is from the first stack and the second one is from the second stack. We should the two stacks. The name of the two stacks are G and S. Okay, the first stack is G. The second stack is S. So the 1 is from G, 2 is from S. But let's see the third test case. 1 comes, then 2 comes, then 3 comes, then 1 leaves, then 2 leaves, then 3 leaves. There's nothing we can do. There's no way that we can assign them to two stacks that these arrivals and leavings make sense. There's nothing that we can do in this case. So we have two stacks and we have this set of arrivals and leavings, and we have to assign them to these two stacks. For each one of them, we have to say if this one is in the first stack or if this one is in the second stack, such that each stack is really a stack and it makes sense that how they come and they leave. Does it make sense? Let me know if you have any issues with this statement. So we have, as we said, we have n items. We have n items. Let me go. It's weird. We have n items that they arrive in order. They arrive in order, in some order, and they all come in somewhere and they leave it somewhere. For example, 2 comes here and leaves here, and then 3 comes here and leaves here, and so on. These are the items that we have, and we have to allocate them to the two stacks. Is the statement clear completely? So now what we can do is this. First, we can say that for each two items like x and y, if they come like this, x comes, then y comes, then x leaves, and then y leaves, they cannot, in this case, x and y cannot be in the same stack. So if the one that arrives sooner leaves, I mean if the ones that arrive sooner comes, then the other one arrives, and then the first one leaves, and then the second one leaves. In this case, they cannot be in the same stack. In this case, I put an edge between x and y. You know, this problem was not very easy problem. Even if you see the standing, not so many people have solved this problem, but it's mostly because they didn't look at this problem like this. If you look at it like this, it would be a lot simpler. I mean, if in this case, we know that x and y cannot be from the same stack, so we put an edge between x and y. Otherwise, x and y can be in the same stack. I mean, otherwise, either if it is x plus x minus x, then plus y minus y. Or if it's the case that we have plus x plus y minus x. In both of these cases, they can come with each other. So if there is an edge between two of the vertices, it means that those two cannot be from the same stack. If there is no edge, they can be in the same stack. So if there is an edge, they can't be. There is no edge, they can be. There's no problem. At the end, the only thing that we need to check is that if this graph is bipartite. If the graph is bipartite, the point is that if it is bipartite, we can put one of the parts in the first stack and one of the parts in the second stack, and they're completely okay with each other. No two of them have any issues with each other. But if it is not bipartite, in any way that we put them into these two stacks, two of them will have an edge to each other in our graph, which means that they cannot be with each other. So we cannot do it with two stacks. For example, in the third case that we saw in here, 1 and 2 need to have an edge to each other because 1 comes, then 2 comes, then 1 leaves, then 2 leaves. That's exactly the case that we discussed in here. This bad case. X comes, Y comes, then X leaves, and then Y leaves. So between 1 and 2 there's an edge, between 1 and 3 there's an edge, and between 2 and 3 there's an edge. So it's bad. I mean, all three of them have an edge to each other, and we have a cycle of length 3. So it is not possible because it's not bipartite. So in this case, it is not possible. But in the rest of them, you see that the graphs are bipartite. In this one, there's no edges. In this one, there's only one edge between 1 and 2. So we just need to add these edges. The only thing, I mean, this ritual was very recently. I mean, it's around 10 days ago. And as you can see, we just first get everything. We just find the numbers, and we see that when num arrives, when num leaves. And then we say that if I leaves before j, I comes before j, and j comes before I leaves, and I leaves before j leaves, then we add an edge between I and j, and then again we find out if the graph is bipartite or not, and what are the parts. And after that, if it was not bipartite, I mean, if call of in here I say if call of u not equal to 3 minus call of u bad is equal to true. If bad was true, then see out that it's not possible. Otherwise, we have a 4, and we say that if call of a was 1, then see out g, otherwise see out s, and see out \n at the end. So this way we can solve this problem. Is this one also clear? If you have any questions about this one, you can also let me know. Nice. Thanks. That is nice. I hope that you enjoyed this live stream. Can you guys rate it from 0 to 10? And give me all your ideas about the live streams. What do you think we can change in the future live streams? I think it's completely okay if you are being critical. I would really love that. I mean, my main purpose is to improve what I'm doing, because at the end of the day, what I need to do is to improve the thing, because if I improve, then everything is going to be better. It can help you a lot more, etc. So feel free to be critical and mention any issue that you see in the live streams, and let me know about them if you think of anything. So I would love to know your honest feedback. If you want, you can give a rate from 0 to 10 to it. If you want, you can just explain that what things you think that might be changed. Which live stream to watch? Yes, I recommend to you to watch this playlist. I mean, all my topic streams are in this playlist that you can watch. There are just simple starting from graphs and DPs. I mean, in both of them, I started from scratch, and I've covered. I tried to cover everything from the scratch, and we're gonna have more sessions, and we will move on to more advanced topics. Speaking in a mic, yes, that's completely okay. I agree with that. I had a microphone. Then I bought a better microphone, but that better microphone was not working well. And now I'm not using that new microphone, but I'm not using my old microphone anymore as well, because I removed it from here. So right now there are no microphones. And that's bad, that's really bad, I totally agree. Maybe I should at least for now bring back my previous microphone that I was using previously. Thank you very much. Yes, sure. I can also cover some simpler topics as well. Sure. And guys, I would appreciate it if you can share this live streams with other ones who might benefit from it, I think it would help a lot for my work to be more recognized. And so if you want, I would appreciate it if you know some other people who might benefit from these live streams and share it to them. You can also like this live stream, and that would also automatically make this live stream to be seen by more people. And there are no homeworks, but if you want, I will share some problems in our Telegram channel or our Discord server. I strongly recommend everyone to join Telegram. I know that a lot of people do not have a Telegram account, but I strongly recommend everyone to join Telegram. That's a very awesome platform for messaging. And I'm not sure that you have heard about its founder, Paul Durov, and what happened to him. I really like Telegram, and I also like its founder, Paul Durov. So I really recommend you to join Telegram. I think you won't, you will be satisfied with it. It's really good. And maybe I can share the problems in the Telegram channel. I can also share it in the Discord server. So if you need, yes, I can make some problem sheets and put them there. Yes, sure. We will do more DP problems as well in our next live streams. As I said, the next live stream is going to be on dynamic programming, problem solving. So, any other questions or comments? Telegram link. It's in the descriptions of the video. I will also send it in the chats. This is the Telegram link. This is the Discord server. Wait a minute. And this is the subscribe link if you want to do that. So, yes, I tried to explain how to implement everything, so that even if you're not familiar with how with the implementation and how you can implement things, I try to implement them. Purpose of Discord and Telegram. If you mean why both, well, some people are more comfortable with Telegram, some people are more comfortable with Discord. But if you mean that why do they exist, this is our community servers, and there are a lot of people there. There are around 1,500 people in Telegram and around 3,000 people in Discord, and people can talk to each other there. I mean, if you have a question, others can help you. I will also try to see that what is being talked in those servers and in the channels. So maybe sometimes I can respond. I sometimes put votes there to what to cover in the next live streams, etc. So that's sort of like our community servers. How can I become newbie to pupil in Codeforces? I have made a great video about it. I mean, I should not say it. I say that it's great by myself, but anyway, I try to cover everything that is important in order to get out of newbie. I have two videos that are very important. First of them is that what you should never do if you are a newbie right now. I strongly encourage you to watch this. This video is about the things that you should not do if you are a newbie right now. And this one is the things that now you should do instead if you want to get out of newbie. I strongly encourage you to watch these two videos. These are really important. If you're writing a newbie and you want to get out of newbie, I strongly suggest you to watch these two videos. I shared the link with you in the chat. I shared the link of these two videos. Is it okay? Or do you have any problems with that? Participate in ICPC, right? Yeah, we will talk about all of this in the future. I myself are going to participate in ICPC the next week. I mean, this Friday we will leave here to Kazakhstan to have our ICPC World Final. So I myself have ICPC very soon, very soon. It's just in 1 week. And we will talk about ICPC as well. If you want, I can make videos about the specialist to expert as well. I have a lot to say about that as well, but I haven't made the video yet. But if you want, I can make those videos as well. Okay. Any more comments or questions? Don't forget to tell us about your ideas. Also, guys, if you can comment under this video, I think that would be great as well. I think comments under videos can really help as well. So if you want, you can also, I would appreciate it if you put comments under this video as well. These videos, yes, are going to be saved in my channel, and whenever you want, you can access them. They will be in my channel forever. So whenever you want that, you can access them in my Telegram channel, in my YouTube channel. And let me send you the link of the playlist again. You can always watch them in this playlist. In the playlist, all the recorded version of all the live streams will be saved. Yes, it is gonna be my only participation in ICPC, yeah. Yes, so I hope that we can perform well in the ICPC. Today we're gonna train for that as well. Today we're gonna participate in another gym to train for that. Okay, I tried to do something for AdCore. I will think of what we can do about the AdCore one. The next ICPC is next week. If you mean the ICPC after that, I'm not sure, I don't know that. But this ICPC that is coming is in the next week. Okay. No, I'm not the one who couldn't enter Egypt last year. No, it was my friend who is also in UMD. I mean, yes, that person was from the UMD team. He's also in UMD, and he couldn't, unfortunately. Ali couldn't enter Egypt last year. But in IOI recently, Iranian students could go to Egypt. They couldn't participate, but after that, they participated online, but for the ceremony, etc., they finally got their visa, and they could go to Egypt. Right now, they are in Egypt, and that's very good. I hope that all the political issues, etc., will be resolved, because it just sucks. I mean, there's no reason for that. That some people cannot enter the other country and participate in competitions like IOI or ICPC. Okay, I will talk about those things for sure. If you want, you can also ask your questions in the Telegram channel or in our Discord server as well. We will cover about ICPC. I will make a dedicated video for it. Okay guys, I hope that you enjoyed these live streams. And you learned something. It was so nice having you here today, and I hope to see you next time as well. Thank you very much. Goodbye.